The chain rule is so very, very important, but easily forgotten, I found by calculus students. It has to do with when we have composition of functions. So hopefully you recall that a little bit. A composition of functions f of g is when you have one function inside another function, which is explained here in math notation. So you have a function of u, and u is a function of g. So you have f of g of x. If u is g and f is of u, then f is of g. It's a composition f of g of x. To differentiate these things, the derivative with respect to x of this composition, we have to differentiate each piece of the function, but it doesn't work as a straightforward, it's not just like free for all differentiate everything that you can see at the same time. But there's an order. We're going to take the derivative of the outside, the derivative with respect to x of f of x, f of g of x rather. That inside part stays alone. And then multiply that by the derivative with respect to x of g of x. So it's the derivative of the outside times the derivative of the inside. So I think of this as like when you were little and your mom used to ask you to help wrap presents, and she would have you put your thumb over the knot. She would tie one knot and then you would put your thumb over the knot, so that there's the knot. We're going to hold down that g of x, take the derivative of the outside, and then you pick up your finger when she ties the second knot to keep it tight, and we'll differentiate the inside. So some people call it the outside-inside rule. And so I think the best way to do it is just look at a lot of them so that you can see how the pattern works. So here's a function y. It's a function inside another function. So if you can picture covering up that 4 minus 3x to the 9. So that 4 minus 3x, it fits pretty nicely underneath your pencil or your fingers. That's an inside of another function. So y prime means that we differentiate the outside first, like we have to peel off the layers of the derivative. By the power rule, the 9 comes down and the 9 goes down to 8. So that's the derivative of the outside. The inside stays the same, 4 minus 3x. And then once we got that outer layer differentiated, we can multiply by the derivative of the inside. So now multiply out here by the derivative of 4 minus 3x, which is negative 3. So here we had the derivative of the outside, or the outside prime, right? Derivative of the outside times the derivative of the inside, or inside prime. And then we just clean it up. So negative 3 times 9, that's negative 27 times 4 minus 3x to the 8th. That's the full derivative. This works anytime we have parentheses or anything that we can really cover up with our finger. For this example, x over 2 minus 1 is a nice little inside piece. So that thing is the inside that will differentiate after we get the outside. Y prime is negative 10 times the inside stuff to the negative 11, right? Negative 10 minus 1 power. The inside stays the same, don't touch it. Remember, you're holding it down with your thumb, and then multiply by the derivative of the inside, which in this case, the derivative of x over 2 minus 1 is 1 over 2 by the power rule. So if you're still thinking about that, I really hope you've done enough practice that you're not having to make too much thoughts and this is becoming more automatic. But that's the inside function. So when we differentiate it by the power rule, you can think of it as x to the 1. 1 times 1/2 is 1/2. X to the 1 minus 1 is x to the 0, or 1. So that's negative 10 times half, 5, negative 5, x over 2 minus 1 to the negative 11 power for the derivative. And we'll leave it just like that. So parentheses with exponents are really good applications of the chain rule, easy ones. So are radicals. We have all this stuff inside. then it will have a derivative, and then we have this outer layer, which is the square root. So maybe you rewrite it as 3x squared minus 4x plus 6, all raised to the 1/2 power. So the 1/2 stuff is outside, and the inside stuff is this long bit. That can help us apply the chain rule. The derivative of the outside power first, 1/2, times leave the inside alone and subtract 1 from the exponent, negative 1/2. Inside stays the same, 3x squared minus 4x plus 6. And then finally, once we peeled off that outer layer, we took the derivative of the outside, we can multiply by the derivative of the inside. 3x squared turns into 6x, negative 4x is negative 4. And now we have that y prime is 1/2 times 6, 3x minus 2 times 3x squared minus 4x plus 6 to the negative 1/2 power. That's a fine way to write it. You might think it's 3x minus 2 over the square root of 3x squared minus 4x plus 6. That's also the same. They're equivalent. I probably wouldn't invest the time in doing that though, because if we had to differentiate again, just as soon do it from there. So those are exponents and radicals, which are basically rational exponents. We also can apply the chain rule to trig function derivatives. These guys are ripe for chain rule because they have these like automatic little inside pieces inside the argument of the chain rule. There's no getting in there directly, but when we do the derivative of the outside, we can multiply by the derivative of the inside. So let's try. Y equals the sine of 3x turns into y prime. The derivative of the outside, the derivative of sine, is cosine. Keep the inside the same, so the argument of cosine is still 3x, and then multiply by the derivative of that inside. The derivative of 3x is 3. So times 3. That means y prime is 3 cosines of 3x. You'll start to recognize this pattern the more you do them, and then you can let that like derivative of the inside stuff kind of float out front. But for now, I'm going to continue writing it in the back and then rewriting it simplified. If you're ready, write the chain rule derivative out front. So the derivative of tangent is secant squared. The inside stays the same, secant squared of 5x squared, and then multiply by the derivative of the inside. The derivative of 5x squared is 10x. Now we can simplify. Y prime is 10x times the secant squared of 5x squared. And we are spent.